All right. You've heard these words before. I know that you have. Centripetal and centrifugal forces. And so they're very confusing. They sound very similar and people use them all the time. But what's the difference? And I'm going to explain everything to you. And I'll tell you that the punchline is it's all about fake forces. And that doesn't make any sense right now, but that's fine. So let's start with the video. This is a video of me driving my old truck. Yes, that's paint scratched on the top. That's fine. I got it really cheap. But this is also why you should get a drone. Okay, I just like this picture. But here I am driving in a circle for you. Yes, I drove in a circle in an empty parking lot just for this. Okay, I used it for some other things too. So how do we explain the motion of this object moving in a circle using forces? So let's start with the very fundamental nature of forces. Here is an older video. Now, so these are fan carts. They have very low friction, and the fans on them exert a constant strength force. I have two of them, but that doesn't matter. I just wouldn't want to redo it. So here, if I turn on the fans and I let them go, what happens? They don't move at a constant speed. They speed up. They increase in speed. They change their speed. What if I turn them around and I push them? So now I'm going to push them. They're moving to the right, but the fans push them to the left. What happens? Come on, Brett. Get it together. Now, there's two for different reasons. Okay. They're moving again, and they change speed, and that's the important thing. A force does not make something move at a constant speed. It makes something change speed. So that's the key. Forces change the motion of an object. If you have a constant force on an object, that means a constant acceleration. Technically, it's not force, it's the net force. So you can actually have a force on an object with no acceleration. If you have two equal and opposite forces, that would produce a net force of zero. But I don't want to get into that. I just don't want to be wrong. It's because, So force is a vector. That is important. So a vector means that it has pieces in multiple dimensions. So there's an x, y, and z component, or just x and y in this case if you want. This is called Newton's second law, and I'll show you that in just a second, but I just want to point that out. And the definition of acceleration is the change in velocity. It tells us how the velocity changes. So here is Newton's second law as an equation. So the arrow over the symbols means it's a vector. So if F net is a vector, acceleration is a vector. Mass is not. But the mass just says what is the ratio of acceleration and net force. Okay. This is the definition of acceleration. The delta, the triangle, means change in. So this is change in velocity over the change in time. But velocity is a vector, right? And so just for completeness, the velocity is the change in position. We usually use r for the position over the change in time. Position is also a vector. Okay, so how can we find out something about this acceleration for an object moving in a circle? Here's another drone video, and this is me. I taped this soccer ball to a string, and that's a yardstick if you need that. So I'm swinging around in a circle. I really like this video, to tell you the truth. The shadow and everything. So let's take this at two different times. I don't know what I'm doing now. So here is a screenshot of the ball moving around in a circle at some instant. And the motion of the ball is directly in the upward direction on the screen. It's moving tangent to the, or perpendicular to the line that's making it move in a circle. And if I look at it a little bit later, it's right there. So it has the same magnitude velocity. The length of the arrow V1 and V2 are the same, but it's in a different direction. So if I use these two vectors to find the change in velocity, I can move them over here. So there's V1, there's V2 starting at the beginning. So the change in vector V1 to V2 is going to be this arrow right here from the end of V1 to the end of V2, and that's my change in velocity. That's delta V. Notice that the direction, that one, the speed didn't change. Two, the velocity vector changed because it changed direction, and the direction of the change in velocity, which means the direction of the acceleration, is towards the center of the circle that they're moving in. That's important. Here's another picture that has nothing to do with anything except I think it's awesome. So that I took a picture of the video every, 10 frames or something like that, and I put it all together, and I just like this. A couple things that have nothing to do with this. Well, maybe. After you let go of the string, the ball moves in a straight line. That's kind of cool. If you look at the distance between the ball and the shadow, you can actually get a value for the vertical position of the ball. And I did this. I'll try to remember to include a link to that analysis in the link down below, but it was really fun. So how do I find the magnitude of the acceleration for an object moving in a circle? I know the direction is towards the center of the circle. So here's the ball, and then here it is a little bit later, and let's say it moved an angle delta theta. Okay, and there's the radius of the circle r. So I have a little thing there. There's v1, there's v2, there's v1 minus v2 right there, and this is delta theta, and there's delta v. So if I need delta v because that has to do with the magnitude of the acceleration. I need the magnitude of delta v. I don't care about the direction. I just need the magnitude. If I look at that triangle with delta theta, delta v is like the arc length of two radiuses, v1 and v2. If delta theta is really small, then delta v is the arc length. Okay, if you make it a really big theta there, then the delta v is not the arc length. But if you use the arc length, then I can find the value of delta v. It's just v1 or v2, it doesn't really matter, they're the same length, times delta theta, and where theta would have to be in radians. Okay, that's just the arc length formula. Now I have this definition for the angular velocity. It tells me how fast the angle is changing. So it's the change in theta over the change in time. And if you play around with this, you can also show that this is the speed, the velocity, not the vector velocity, the vector magnitude divided by the radius. If I use that, I can substitute in for delta theta. So I get the acceleration is the change in v over the change in time. Delta v is v delta theta over delta t, which is v over r. So I get v times v over r, or v squared over r. And that is the acceleration, the magnitude of the acceleration for an object moving in a circle. So now we're ready for centripetal force. And I have another composite picture just because I feel it's like an artistic statement. Okay, so you don't have to appreciate it. It's for me to express myself. So centripetal literally means center pointing. That's what that word means. It's a center pointing force. It's the force needed to make an object move in a circular motion. So that's mass times acceleration, where acceleration is v squared over r. I should have put that in here, but I didn't. So since the acceleration depends on the radius, if I have a smaller circle, if r gets smaller, the acceleration gets greater, so I'd have a higher acceleration and a higher force. If I go faster, I'd also have a higher acceleration. Tension. Tension is a centripetal force. If you go back to the picture of this ball swinging around, what force made the ball move in a circle? It was the tension in the string. But we call that the centripetal force. So centripetal force is just a label that we put on different forces that make it move in a circle. What about the car moving in a circle? Friction. Friction is the force that makes it move in a circle. The friction points toward the center of the circle. Without friction, the car would just keep going in a straight line and crash, and that'd be bad because that's my truck. Okay. So that friction is the centripetal force. And you can actually have a combination of forces or even a component of force be the centripetal force. Okay, we're done. Halfway. Centripetal force. Centrifugal force, we're going to start talking about elevators. And I took this picture. This was put up in our building on the elevator, which is a terribly slow elevator, not very useful. But, you know, the pandemic and social distancing and it's peeling off. I don't know. I like this picture. That's all. So let's look at a video. This is a video I took a long time ago, and we were at a conference in New Orleans. I'm going to play it multiple times. And this is in the Hyatt Regency in New Orleans, which is a great building with a super fast elevator and a glass elevator. So I got a bunch of friends together, and I'm in that elevator. I'm wearing on the left. There's some rando guy on the right. Actually, I think I do know that guy. And so I'm with my friend Dwayne, and I got my friend Eric to video from outside the elevator. Now, as we are going down, Dwayne tosses the ball. So the elevator is accelerating up, actually, because it's slowing down, and he tosses the ball. So I get two views of this motion. I get the view from inside the elevator, where I can see the ball, and I get the view from outside the elevator. That's pretty cool, huh? I like it. So if I look from outside the elevator and I plot the motion of the ball in each frame after I've scaled the frame, I get this parabolic graph. The other curve, the one that curves up, this is actually for the tossed ball as the elevator was accelerating up. Not, well, it was moving up too. Okay, so this is a different video, but same idea. So as the ball goes through the air, if I fit a quadratic equation to that, which I did, the term in front of t squared is negative 4.9. If you consider your kinematic equations, that should be 1/2 times acceleration. So if you multiply negative 4.9 times 2 to get the acceleration, you get negative 9.8 meters per second squared. That is the acceleration of a free-falling object. That works. Okay, now if you think about how high did it go in the elevator, you'll notice that the elevator is accelerating when you toss the ball. So it doesn't land at the same place because it comes back to because the elevator moved while it was in the air too. Okay. Now, what if I'm inside the elevator? Here's a video from inside the elevator. Again, I fit a quadratic equation to the motion of the ball, but you'll see the A term is negative 5.39. So that gives an acceleration from inside the elevator of negative 10.78. So these accelerations do not agree. But here's the problem. If you think about Newton's second law, I have in the y direction negative mg, and that equals mass times acceleration. So the acceleration should be negative g. It should be negative 9.8. So the one on the left works. The one on the right does not work. So if you look at the forces inside an elevator, from outside the elevator, this is a picture. The elevator is accelerating up. There's only one force acting on it, the gravitational force. And so you get the acceleration is g. This is a reference frame from outside the elevator where it is not accelerating. This is called an inertial reference frame. Okay, this is where we make our Newton's second law work, in an inertial reference frame. But what if I'm inside the elevator and it's accelerating and I want Newton's second law to work? Okay, it doesn't, because I know the acceleration is greater than the gravitational field acceleration. In order to make that work, I have to add in an extra force, and this is a fake force because it's not really an interaction between two things. It's just fake. Okay, so this is a non-inertial reference frame, and in order to make Newton's second law work, I have to add a fake force, and the fake force is proportional to the acceleration of the reference frame. So it's actually negative mass times acceleration of the reference frame. Okay, so someone wants to say things about Einstein's equivalence principle, and Einstein, yes, I'll just go ahead and say, I should have included the picture. Einstein says, well, you can't really tell the difference between gravity and acceleration of a reference frame, and that's true. So some people would solve this by saying, oh, I'm just going to put a greater gravitational field, and it'll give the same answer. It gives the right answer, but it's a terrible way to do it. That's just my opinion. Okay, so here is another video. This is inside my truck, driving around the circle, and I have this mass hanging down, and you'll see that it doesn't hang straight. How do we explain that? So if I am looking from outside the car, I see gravity's pulling down on the mass. I got that. The tension in the string is pulling up, and tension, the strings are flexible. They can only pull in the direction of the string. So the tension is up in the same direction. There's no way to add these two forces together and have them cancel. So it does accelerate. The vertical components can cancel, but we're going to be left with a component of tension to the left, so the mass is going to accelerate to the left, which, by the way, I'm turning to the left. Okay, so that's the direction of acceleration. So that's why this mass hangs that way. And this is using centripetal force. So now we get to centrifugal force. If I am in the non-inertial reference frame from inside the car and I want this to work, I see the string swings out to the right, and there's what's pushing it that way. Well, I don't know. There has to be something, and it is a fake force because I'm in an accelerating reference frame because I'm inside the car, and this is centrifugal force. So it literally means center fleeing, fugitive fleeing. Okay, center fleeing force. It's the fake force that you need to add in an accelerating reference frame to make Newton's laws work once again. Why is centrifugal force so dangerous? Well, because for learning students, for introductory students, they already have a problem identifying forces. They want to say, oh, it's the force of the motion or the force of something else. And it's important to break down forces in terms of fundamental interactions between two objects. And this is not one of those. Okay, so that's why it's dangerous, because students want to use it and then they use it in a bad way. But sometimes it is useful once you really understand it. If you want to talk about things like tides or, stable orbits between multiple objects, you kind of need centrifugal forces. It just makes things easier. But so it's there. It's a fake force. Fake forces are useful, but they are indeed dangerous. And I will end there. I hope you guys enjoyed that short lecture on the difference between centrifugal force and centripetal force.